Hello everyone. After we've talked about the question number 1, 2, 3, 4 and 5 in the previous video, in this video we're going to start with 6, 7, 8, 9 and 10. I mean the next 5 questions. So for this question number 6, we have a small boat travels at 3 meters per second in seawater. That means the water is not moving, but the boat is moving at this rate. To cross a river 60 meters wide, this is the 60 meter wide, with a current of 4 meters per second. What is the minimum crossing time? Pay attention, please, here. The current that's moving at a rate of 4 meters per second is just like a distraction, because the time here has no influence with the motion of the current. So what we're going to consider here, only the width and the speed of the boat. Okay, so the boat is moving at 3 meters per second. It's exactly the same if the current is moving at this rate of 4. What we know as a formula, the v is just like a distance divided by the time. That means the time would be the distance divided by the speed. The distance here for us is just like the 60 meter wide. The speed of the boat is motioned here as 3. Okay, so if we divide in the 60 per 3, this is giving 20 seconds. The correct answer for this one is gonna be D. Okay, so for question number 7 here, we have a wooden block slides on a rough, this is a rough horizontal surface. It's sliding, let's say, to the right, and eventually comes to a stop at a certain distance. During this process, the friction force on the block, what are the effect of the friction force in this case? So the motion here is to the right. That means the relative motion is to the right again. The effect of the friction would be to the left, because friction are always directed to the opposite direction of the relative motion. So for the A, it says do good deeds. This is a proposition which has no sense. Do negative work. This is the correct one. Actually, we're going to prove it later. No work. We're going to prove it as well. If it's doing a negative work, that means the no work is not a correct answer. The correct answer for us is P, and as I say, we're going to prove it. Do positive work first, then negative work. So as a work formula, we do know it is the force times the displacements, which is the force times the displacements times the cosine of the theta. The theta, for sure, it's the angle between the direction of the force and the displacement. So we've considered the block is moving to the right. That means the displacement is toward the right. The F is toward the left. Those two are making an angle of 180 degrees. The cosine of 180 degrees is -1. That means it's gonna be minus F times D, and the F and D are positive with the minus. This is a negative term. That's why the B is like a correct one. For the C and D, we say it's not, or they are not the good answers. Okay, so for the next one here, we have question 8. It says for a system consisting of two interacting interacting object. If the net force acting on the system is 0, then the system A, conservation of total momentum, conservation of total kinetic energy, conservation of mechanical energy, all of the above are conserved. If we take the Newton's second law in terms of momentum, the net force is just like the change of momentum, or the rate of change of momentum. So what they give us here is, if the net force acting on the system is 0, that means all of that equal to 0. The change of momentum is 0, which means the initial momentum would be exactly the final momentum. Okay, that makes the first answer is the good one, or the right answer. For the B, we have conservation of total kinetic energy. Kinetic energy would be conserved if the collision would be perfectly elastic. In the perfect elastic collision, the kinetic energy would be conserved, but they didn't mention anything about it here. If there would be any internal interaction between the elements of the system, maybe those interactions will change the kinetic energy. So the conservation of total kinetic energy here is not guaranteed. Conservation of mechanical energy. Conservation of mechanical energy, that is true if the system is under the action of forces that are conservative. If all forces acting on the system are conservative, in that case the mechanical energy would be conserved as well. The B, the C are not correct. That means the D is not correct. All of the above are conserved. They are not. All what is conserved here is the total momentum. For 9 here we have which of the following statements is true about power? As shown by P equals W over T, power is directly proportional to work and inversely proportional to time. For P, we have W divided by T. The power is not proportional to the work because of the work and time are dependent. Actually, they are not independent, but they are dependent. That means the work is dependent to the time. What makes this formula is not correct as a statement here. Power is directly proportional to work. This is not actually correct. Inversely proportional to time, and this is not as well not correct. So for A, we can now consider it as a good answer. For B here, as shown by P equals F times V, when the engine power is constant, the traction force is directly proportional to speed. If we take P as instantaneous power equal F times the speed, if we take the power as a constant, the F would be P divided by V. We say the P is a constant. That means the F would be something like K, a certain constant, times the 1 over V. In that case, we see clearly that F is inversely proportional to V. In the case of P is a constant, as we say. So the B as well is not correct in this case. For C here, what we have, the more work done, the greater the power must be. This is not correct. We can get back to the formula here. If the work done is greater than the previous done, the time would be take longer and the power would be constant. It's not changing. So it's not only the work is greater will make the power greater, but the work could be greater or will decrease, and the time in the same time will change. So that makes the P will still as it is. So the more work done, the greater the power must be, is not the good thing to consider. For D, we have the work done per unit time is called power, and this is actually the definition of the power. The power is just like the rate of work. Dividing work by time, this is exactly the definition of power. So the one that we can consider here as a good statements among these four is the last one, the D. So the work done per unit time is called power. Finally, for this video, we have this question 10. Let's just like erase all what I've written here. We have 10. Regarding curvilinear motion, which of the following statements is correct? We are talking about curvilinear motion. That means something which is not a straight line form. For A, it is impossible for an object to move in a curve under the action of a constant force. This is not the good one. If we have or if we are studying the projectile case, if we have a projectile, this projectile will form a curvilinear motion, even though this projectile is under a constant force, which is the weight. The weight of this projectile is the only force that's acting while it is forming this path, which is curvilinear. So for A, we cannot take it as a good one. So it is possible for an object to make a curvilinear motion if it is under a constant force. For B, an object must move in a curve under the action of a variable force. Again here, an object must move in a curve under the action of a variable force. It's exactly what we said in the previous question. An object could move in a curve under the action of a variable force, as it can make a curvilinear motion under a constant force. So the variable force is not a requirement to form a curvilinear motion. Okay, so for the B, it's not the good one as well. For C, we have here, for an object undergoing curvilinear motion, the acceleration and velocity are never collinear. This is actually the best answer to choose. In a curvilinear, let's say a circular motion, the speed is always tangent to the path. For the force, let's say this is the total force. This force has a normal or the one that's forming a right angle with the speed. So the force, which means the acceleration, must have a component that's forming a right angle with the speed, which means if we have the velocity and the acceleration are collinear, that means the objects must be in a straight line motion. So to make this object moving in a curvilinear motion, those must form a certain angle, which is difference from 0 and from 180 degrees. This is the condition. So for the C, we have, for an object undergoing curvilinear motion, the acceleration and the velocity never collinear. This is true. For D, the speed of an object in curvilinear motion must change. In a circular motion or a uniform circular motion, The speed could be a constant. What changes is the velocity. The velocity is changing the direction, means it changes while the object is forming this curvilinear, in general, curvilinear motion. But for the speed, it could be a constant. Just like take a note, the speed is the magnitude of the velocity. So the magnitude could be constant, but the direction changes. Okay, this is it for this part 2 video. As I say all the time, never forget to subscribe and hit the bell just to get notified while I'm posting the next video. In the next video, we're going to start with 11 until the question 15. Until then, take care.